So this lesson is looking at linear regression and testing linear regression. So I'm going to point out there's a couple ways we can calculate that R I mentioned in the last video. So in the last video we just looked at calculating it with the formula, but actually it's something that can be calculated using the statistics functions on your calculator. I've given detailed directions at the end of the notes on that. It can also be calculated on Excel. So really, those are the expected ways that you would be doing for a test, is using your calculator or Excel. So if we're looking at linear regression, that's saying if these things are related, what's the relation? So I've given an example here. If we have a startup cost and cost of producing the item, we can figure out a linear equation to produce this. Now that's considered a deterministic model because we can make this prediction exactly. But lots of times we are going from a statistical model or a probabilistic model where we are looking at the data and saying, well, what is the relationship? So with that, the little hat here, remember, just like with our p hat, means we're estimating. So estimating y using a plus bx. This might look familiar to some of you. If you remember back to your grade 10 math, you would have learned y equals mx plus b, where m was your slope and b was your intercept. So this is the slope-intercept form of a line. So on this, y is still our dependent variable, x is still our independent variable, but a and b are slope and intercept, and actually in your statistical calculator, your financial calculator, those also match to a and b in your calculator. So to calculate these, again, we have some big equations, but typically we use calculators, Excel, or other stats programs. So I'm going to get into those as we do the next part as well, because these kind of get linked together a lot of the times. So testing a hypothesis about a linear correlation. Once we've calculated this, we need to say, can we use it? Are these things correlated enough that it makes sense to make this model and use it to be doing predictions? So a couple assumptions we're making: that we are looking from a random sample and that both variables are approximately normally distributed. One nice thing about these hypothesis tests is they always have the same null and alternate hypothesis. The null is always that there's no linear correlation, or rho, remember that's the population symbol that corresponds to R, is equal to 0. And our alternate hypothesis is that there is significant linear correlation, so rho does not equal 0. When we're looking at these, we do use a t-distribution, and our degrees of freedom is n-2, but there is going to be a different formula for t on these because it's going to depend on that value of r. So a couple warnings here: correlation does not imply causation, so things can be very correlated and one doesn't cause another. I will send you guys some somewhat entertaining examples of that. Also note that if you have, instead of raw data, you've got averages, you can end up with some skewed results that make it appear things are correlated when they're not really. And even when you conclude that they're not linearly correlated, there may be some of those other correlations. Remember, like the curves that we were looking at with the scatter plots. As mentioned earlier, we have this r squared that tells us our explained variation. So our test statistic is calculated using this variable with our degrees of freedom, as I mentioned earlier, being n-2. Same thing that we had before. These are two-tailed tests. So if we end up in either critical region, we reject H0 and there is significant linear correlation. If we do not end up in the critical regions, there is not significant linear correlation. So the knots still go together. So if we look at this first example, you do need to put those values into your calculator. So in your calculator, I've given instructions at the end of the handout how to do it in great detail. Basically, you're still going into that data. Earlier we had used x and we were leaving all the y's as 1s. Now we're putting in values for the y's. And once you have it all, then you can go into that stats and get it to display your slope and your intercept and everything else. So when you do that, your calculator will spew out that the slope is 1.6, minus 8.92, your correlation is 0.913. So I strongly encourage you to pause the video, try putting those values in your calculator to make sure you know how to use the calculator. The steps will be a little different if you're using a different sort of calculator, but this is the calculator that you've been asked to use for this course, so that's why I've given you instructions for those ones. So if we look at this from the hypothesis test, same null and alternate hypothesis we're going to have every single time. So we can take this R value and plug it into that test statistic and come out with a test statistic value that is 3.876. So when we look up in our t-table, it's two-tailed. We're given 5%. Right, so if two tails is 5%, one tail is 0.025, so be careful that you're looking on the right part of the chart. Our n in this case was 5, right? We only have 5 data points, so our degrees of freedom is going to be 3. So when we look that up on our t-table, which we've used many times before, it tells us 3.182, but we know this is two tails, so we have positive and negative. We can see this is above the positive, so it's in the right tail. So we can reject H0 and conclude there is significant linear correlation. Second example here I have using Excel. So we're going to look at this data over in Excel again. So same kind of steps, but we're going to get Excel to give us those totals. So copied that value into Excel, and I will be sharing the Excel file with you guys as well. And so slope is fairly easily done, but do pay attention to the fact that y's have to come first, x's have to come second. So the slope formula, the slope function is just slope, and then we take those two arrays for the y's and the x's. The intercept is also take the y's, take the x's, and it's just called intercept, not y-intercept, but it is the y-intercept. The correlation coefficient is just CORREL. This one doesn't actually matter if you take the y's or the x's first. It gives you the same result either way. Lots of people like to take the y's first so that you have a consistent thing with the slope and the intercept, and that's fine. It'll even tell you your n because you can use the count function. So we can get all those values straight out of Excel. So once we have those values, again, we can take them and plug them into our formulas for our hypothesis test. So no linear correlation versus significant linear correlation. And when we look at these, we plug that in, we get our test statistic is negative 6.90, which is very far down compared to our critical value, the left one being negative 2.819. When we plug it in to that 24 minus 2, so 22 degrees of freedom. So we definitely are in the critical region, we definitely can reject H0, and there's definitely some significant linear correlation between these variables. So all of that is looking at, is there correlation? It again relates back to, I'm going to go way back to the diagrams we had in the first section. Right, these values 0.7 to 1, 0.3 to 0.7, those were sort of a rule of thumb, checking to see. The test is a little more formal and tells us whether we should be using those equations to make predictions. So the last of the videos in this section is going to be looking at how we use those equations to make predictions.
Go to the playground.
So we'll look at using the regression equation in the very next one.